So this series about rocket engines is not really gonna be in three parts. I believe I can finish the rest in this video. So before we proceed further with the expander cycle, we last left off at the full flow stage combustion engine. So stage combustion is basically, okay, so we have one pump. We don't have two separate pumps, right? Like an open cycle or a closed cycle engine. But this time we only have one pump. Of course, it's still being run by a pre-burner, but it's only meant for one propellant, or actually, it can be for both propellants, but it can be just for one propellant. Okay. So we have our turbo pump, and then we have our shaft, and then we have our pre-burner, which spins the shaft. And so our fuel and our oxidizer. And so these guys get pumped into here, but of course, either the fuel or the oxidizer is pumped into this one pump. And of course, that's fed into the combustion chamber and the engine itself. Okay. And of course, the oxidizer and the fuel are fed straight into here. Okay. So in this case, this is a fuel-rich stage combustion engine. While if instead we pump the LOX or the oxidizer in it, instead of the fuel, we have an oxidizer-rich stage combustion engine. Now for a full flow stage combustion engine, okay, so I have two separate pumps. Now for the LOX and the fuel, but instead now we have two separate pre-burners, which are either fuel-rich or oxidizer-rich. So if I don't confuse myself here, we have two pre-burners that spins the entire shaft. And then we have two pumps themselves, one for the fuel, one for the oxidizer. And then now we have two separate pre-burners which are either fuel-rich or oxidizer-rich. So this is the fuel-rich pre-burner. And then this is the oxidizer-rich pre-burner. And then the pre-burners get fed into the engine. And the pumps are, the pumps are fed, or the fuel and the oxidizer that are coming from the pumps are actually pumped right into the pre-burner, or into both pre-burners, so that we have maximum efficiency. So it goes here, and it also, I guess, this branches off into here. So now we have two separate pre-burners, and then that are either oxidizer or fuel-rich, and then we have separate pumps that feed into the pre-burners. So once your fuel and your oxidizer go into the combustion chamber, they're already hot gas. But there will be some fuel and oxidizer that will be fed directly into the combustion chamber, which are mixed and then ignited by the hot gas coming from the pre-burners. So I was able to explain the last video pretty well about what this full flow stage combustion engine is, but here it is. Two separate turbo pumps ran by two separate either fuel or oxidizer-rich pre-burners. So before I talk about the expander cycle engine, we need to talk about heat first. So you may notice, okay, right, we burn these things, right? And since we're burning them, we're working with really, really high temperatures. So we need to worry about dissipating heat and making sure that our engine doesn't melt. Now, how do we make our engine not melt? Well, that's where cooling So the hottest part of the engine is the actual combustion chamber and nozzle themselves. So how do we go on about cooling things? Well, there are many ways to go on about cooling your engine. You can run very, very cold water through the wall of it, but excuse me. But a popularized way of cooling your rocket engine or your combustion chamber is to run the fuel. So we have an inner lining for the combustion chamber, and then we have an outer lining. So there are two layers for the rocket engine. And what is done is that the fuel, which is always subcooled to get the maximum density, is fed into these two layers. So the fuel is run through the engine or between the engine, in the engine walls to dissipate heat. So as the fuel travels along the engine, actually it's fed from down to up so that it's able to be fed easily into the engine. So once the fuel is run up the engine, it cools the engine and is fed into the combustion chamber. So that's one way to go about it. Another way of cooling an engine is through what is called radiative nozzle or cooling. Now this over here is called regenerative cooling. Regenerative cooling. Run the fuel through the engine, literally through the engine. So two layers, fuel is run up that, or run through those two layers. Now the second way of cooling your engine is through radiative cooling. So you have your combustion chamber and your nozzle, but instead this time, they're made of a special kind of material such that when heat is applied to them, they chip away, or they sort of dissipate with the heat. So I guess it partly gets destroyed, but not destroyed enough for the engine to become unstable. So this kind of cooling is called radiative cooling. And in fact, this is used by the SpaceX Merlin vacuum engine because it's more economical, this kind of cooling. Rather than having to create two layers for this, they just need to create the engine out of a very strong, durable material that slightly gets destroyed. But as it gets slightly destroyed, but not destroyed enough for the engine to be unstable, it takes away the heat with it, with the parts that chip off. So actually, the cooling mechanism of the SpaceX Merlin vacuum engine is actually composed of radiative cooling and regenerative cooling, because the main engine itself is actually split into two parts. So this is the SpaceX vacuum Merlin engine. Okay, so it's separated in two parts, which is either regeneratively cooled and radiatively cooled. So we have a smaller chamber liner. We call it a chamber liner. So something like this. And then part of the nozzle is regeneratively cooled, and part of it is radiatively cooled. So the regenerative cooling stops here. So there's a manifold over here, not mathematical manifold, but a sort of pipe that goes around here. So you have a manifold where the engine is, the fuel is pumped through, and then the remaining portion of the bell nozzle is regeneratively cooled. So you'll notice that when you watch the feeds of the second stage in SpaceX webcasts, you'll see that part of the engine is black, while part of it is silver, or the usual color of a rocket engine, right? So this part here is radiatively cooled, And this part here is regenerative. Regeneratively cooled. So these are the two main types of cooling your rocket engine. Regenerative cooling or radiative cooling. Okay. It's a pretty straightforward concept. So now that we know about cooling, how do these different types of engines cool themselves? Well, of course, they run the fuel up here. So the pump is actually there not only to increase the mass flow rate of the rocket engine's propellants, but they also help us run the fuel through the engine walls to cool it. So that's a neat little way or purpose for the turbopump. Okay. So now let's talk about the last type, or at least last type that's known today as of the recording of this lecture. Okay, so once we're done discussing about the expander cycle, we will move on to how engines ignite the propellants, how they even make these controlled explosions. Okay, so so expander cycle. So up until the present, or up until now, or this time, we have been mostly dealing with trying to increase mass flow rate and cooling the engine through the fuel. And also running the turbopumps by using a pre-burner or a small tiny rocket engine that spins the main shaft of the entire turbopump system. So I forgot to mention this, but the entire system with the pumps and the shaft and the pre-burner, all this is called the turbopump system. Okay, so, right. We have our shaft, we have our two pumps, yada yada, I know that. But okay, we know that when we ignite the propellants, we get really hot gas that's moving really, really fast. So what if instead of using a tiny rocket engine, which would probably bump up costs, what if we just pipe the exhaust off the engine and use that exhaust to spin the turbopumps? So now we have a small box or a small place for the hot gas to pass through. We have our combustion chamber. Okay, so fuel oxidizer. Run the fuel through the engine. So part of that fuel gets pumped into the engine, and now, or actually all of it's pumped through the engine. And then the oxidizer is also pumped through the engine. So now what we want to do is make a small tiny duct here that feeds into this shaft spinner chamber or something, however you call it. And so now, there, it spins the turbo pumps, or the thrust of the engine, or the hot gas in the engine, is the thing that moves the pumps. Now, like all of the cycles of the rocket engine, this produces a really, really this presents us with a chicken and egg dilemma. How do we even start the engine here? Well, of course, we would, for this case, I believe we would have one small rocket engine that would temporarily run the pumps, and then once we get the engine up to speed, we just shut off the small tiny pre-burner. Oh no, here it comes again. Okay, so this is the expander cycle engine. We use the hot gas from the thrust chamber to spin the turbo pumps and increase the mass flow rate of the propellants. Okay, so now we've discussed the different types of rocket engines. What is the tactics used by these rocket engines to combust their propellants? So, alright, we've talked about of course, injecting it. It's simply we simply have a disc or a small cake-looking like cylinder with a bunch of holes in the bottom, optimized such that the fuel droplets and the oxidizer droplets hit each other at just the right moment. It's called atomization. So they hit each other at just the right amount and at the right angle, such that when we combust them, we have optimal thrust or hot gas spewing out of our rocket engine. So how do we even ignite these propellants? How do we go on about actually making the explosion that we wanted to set out to do? Now there are many ways to do it, and in fact, sometimes we don't even need something to combust the propellants, because there are certain propellants wherein when we do mix them, they combust on their own. So for the rocket engines that uses these kind of propellants that combust on their own when we mix them, they're called hypergolic. Hypergolic propellants. So hypergolic propellants are propellants such that when you mix them together, they combust already. Now the problem with hypergolic propellants like hydrazine is, I'm going to say here, example, EX hydrazine. So the problem with hypergolic propellants is that they're very, very toxic to us. So you really have to wear really protective gear when you deal with these kind of propellants. Okay? So another way of igniting rocket engines is through a mixture.
I'm just watching.
Pass behind the camera for Christ's sake.
I'm just watching.
It's not funny anymore, Chen. I'm serious.
I'm just watching. Don't worry.
Okay. If I'm not gonna get any more interrupted,
Yeah, I'm
a
looking.
second way of igniting your rocket engines is through a spark plug, like how you ignite a car.
Oh, sorry.
A spark plug. So, like how you'd ignite a car's combustion chamber to spin the pistons, here we use a spark plug to ignite the engine's pre-burner to get things up to speed. And of course, sometimes you'd put the spark plug in the main combustion chamber to ignite the engine itself. Of course, okay. So now this is used by the SpaceX Raptor engine to ignite their Methalox engine, or the Methalox mixture. Methalox is just methane and liquid oxygen. Sometimes we use shortened names, like, okay, RP1 and LOX is Kerolox. Of course, methane and liquid oxygen is Methalox. Hydrogen and liquid oxygen, or LOX, is Hydrolox. Now these are the most common propellants used in rocket engines. Kerolox is used by the Merlin engine, Methalox is used by the Raptor engine, Hydrolox is used by the RL-25 engine or RS-25 engine, made by Rocketdyne to power the space shuttle. Okay, so apart from spark plugs and hypergolic propellants, there are certain, especially Kerolox here, and the SpaceX Merlin engine, how they ignite their propellant is through using another liquid. So, liquid igniter. Liquid igniter. Now, for Kerolox engines, or for the Kerolox mixture, we ignite it using TEB. EXTEB, or triethylborane. Yes, this has become chemistry now. Triethylborane. Now the thing with triethylborane is that once it comes into contact with RP1 and liquid oxygen, or just RP1, it ignites. So this is used, of course, by the SpaceX Merlin engine, because the Merlin engine uses Kerolox. So either the C engine or sea level engine or vacuum engine uses Kerolox, and then they use TEB or TEB to ignite the propellants. And for others, they use another one here. I think this is triethyl ammonia, T-TEB. We got this A part. I don't know if it's triethyl, but then there A part. Other engines, like I think used by Hydrolox engines, they use the T-TEB mixture to ignite the propellants. So in summary, the three main types of igniting your propellants in your rocket engine is hypergolic. So your propellants already combust by coming into contact with themselves. Spark plug, wherein we use a spark plug like we would use in a car to ignite our preburners or our rocket engine, or the fuel and the oxidizer inside the combustion chamber, or liquid igniter, wherein we have a separate third liquid which we use in just the right amount, of course, to conserve them, to ignite our propellants. And so, before I conclude this chapter on the rocket engines, let's talk about nozzle size. Because the thing is, nozzle size is very, very important, because pressure is a contributing factor to your thrust, to the thrust of your rocket engine. So if I'm not wrong here, we recall that your delta V is equal to your exhaust velocity times the natural log of your dry mass over your total mass. So if we just do a little bit of algebra, we will see that our exhaust velocity for our rocket engine is equal to our delta V over the natural log of our dry mass over our total mass. If you know your delta V and then your mass ratio, we call this the mass ratio, then we know our exhaust velocity of our engine, or our engines. Now the exhaust velocity of our engines, or when we talk about the other delta V equation, which is the one that me over mt, the one where it uses ISP and gravity. ISP here is only counted for one of all your engines. So for one stage, we only calculate delta V's of one stage only. When we have one type of engine, right, we only use one type of engine per stage, of course, and we'll get to that, about what type of engines we use per stage. We only count ISP in terms of one of the engines, not all of them. So let's say your sea level Merlin engine is 400 seconds worth of ISP. Or let's say it's 400 seconds. Now, let's say that you have 8 of those engines in your stage. Now, we don't say that the ISP is 32 or 320, if I'm not mistaken, or no, 3,200. Yeah, if I'm not mistaken. Yeah, that's not going to be it. The ISP is only accounted for one engine among all of them. And it practically speaks for all of the engines already. Okay, so let's talk about optimizing your nozzle length and diameter. Now, we're not going to go into weeds here. We're just giving a high-level view of optimizing your nozzle. So, on sea level, which is 0 meters, we have a certain pressure, so one atmospheres, and that contributes to all the gases on Earth that are going down in your engine, right? And since it's going down in your engine, right, so there's always gas around us that's pushing on us, 1 atmosphere pressure precisely, that's also pushing on your rocket engine, and so when the hot gas pours out of your rocket engine, or moves out of your rocket engine, the pressure also affects it, okay? And that could affect your engine efficiency. So there are 2 cases wherein you do not want your rocket engine to experience. So the first one is called under expansion. So this is when, all right, what you want is this kind of flow. So it's just a steady flow of gas. But under expansion happens when the pressure exceeds your exhaust velocity or your exhaust pressure. So it starts bumping into each other and forming these hourglass things. And you'll notice that there are some like diamond-looking things inside these flame sort of tubes. It's called mock diamonds. And then we don't want this to happen because some of the thrust is dissipated this way, some of the thrust are dissipated this way. We want the thrust to all go down this way. And this happens because the pressure is moving in both directions. It's counteracting or actually moving the thrust in both of these directions, the hot gases. So the pressure is affecting them. Some that go this way, some that go this way. And they cross in the middle in these beautiful mock diamonds. In fact, this happens in the SpaceX Raptor engine, though it's not much of a problem. It shouldn't be much of a problem. It's just when you want to make your engine efficient, when we're at sea level, we want the nozzle to be as small as possible, but not very small to the point we won't produce meaningful thrust or our gas is not in the right direction anymore. So this is under expansion. And of course, you're already guessing by now. You can guess by now. The next thing you don't want your rocket engine to experience is overexpansion. So rocket engine, thrust chamber, overexpansion. So this is when, this time, the pressure doesn't affect your thrust at all. So it can practically move in any direction. It can go anywhere it wants to. So now, this time, like a light beam that is continually spreading out, this time your thrust is spreading out too much. So because your rocket engine's bell nozzle, or your nozzle in general, is too small, your thrust is going wherever the hell it wants. The hot gas goes wherever the hell it wants now. Because the purpose of your nozzle, if you recall from the last lecture, is they direct the thrust in the direction we want the thrust to go, or the hot gas. They move the hot gas, or they tell the hot gas, go this way. You know, physically, they tell them to go this way. Some hot gases don't want to move to, let's say the left of the engine, or the lateral axis of the engine. The nozzle tells them, hey buddy, stop. You're supposed to go in this direction, instead of go that direction. Okay? And now, since your nozzle is small, there are some gases that are freely able to move in the lateral direction, go here or here. So that is overexpansion. Neither of these scenarios do you want your engine to experience. You want a clean, straight combustion. So the ideal way for your rocket engine to fire is like this, straight, nice and beautiful. None of these guys are going in any other direction rather than downwards. So this is the optimal configuration of your thrust. Now, to counteract under expansion, what we want to do is shorten this time. Shorten our nozzle. So make it shorter. When you're at sea level, or when you're in an atmosphere with high pressure, you need smaller nozzles. While you're in space, since you don't have pressure, or you practically don't have any pressure at all, you're gonna want your nozzles to be big. So I'm gonna write here, solution, bigger nozzles. And this is why you'll notice when I drew the SpaceX Merlin vacuum engine, the nozzle was actually pretty gosh darn big, because that's their solution to overexpansion. And this is part of the reason why rockets are in two stages. Because if we only have an SSTO, we need an engine that is ready to switch to the solution for underexpansion and the solution to overexpansion. So yeah, so solution, bigger nozzles. And for the under expansion, our solution, smaller nozzles. Okay? And if your engine's ready like this, you don't need to change anything. No change needed. Now there's a special type of rocket engine nozzle or type of rocket engine that partially solves this problem of over and under expansion. And this is called the aerospike nozzle. Now there are two types of these aerospike nozzles. There is the toroidal, not toroidal, it's toroidal spike version where it's a cone, and then there is the linear aerospike, which is like, it's like a curved type of triangular prism, let's say, or tent like thing. So this time the thrust is run along this. So it's like a reverse engine. Now what the aerospike solves is that it's like a one size fits all type of nozzle for expansions. The good thing about this is that when you're in a pressurized environment like on a planet like Earth, the pressure does the work for you of shaping and directing the thrust. So when the hot gas moves along the aerospike, the pressure moves along it, the pressure, of course, is acting on the engine. So when the hot gas moves out, the pressure shapes it, and it's going straight, and that's good. That's what we want. Now you'll notice that some gases are not gonna travel along the spike, and that's okay. That's perfectly fine, so long as the gas doesn't go here. And actually, the aerospike prevents the gas from going this direction or greater than this direction. So we don't have over expansion or under expansion, or actually under expansion. But the pressure doesn't quite affect the gas once it leaves here. That's a nice phenomenon associated with aerospike engines. That when the gas exits the cone, or of course the tent here, they get shaped into these beautiful, sharp spikes. Very hot, sharp spikes that will melt your face off. Okay, so yeah, same thing here, but instead they're just going here. They're not in all 360 degrees of the engine right here. This is actually easier to cool than this one here, because you have to worry about, oh well, how the heck do I run the fuel through here if I can't run a pipe through here because the very hot gas is gonna affect the pipe. So it's sort of a problem here. But for this kind of engine, you can just run the fuel through here and then out through here, because the thrust is only going in this direction, or it's only here. It doesn't have to really go this way. Yeah. So one of the planned spacecraft to replace the space shuttle, such as the Venture Star, actually planned to use this. And if the Venture Star continued, we would have seen this type of rocket engine, lift a rocket into space, or lift a rocket into space. These kind of engines, aerospikes, are really something that looks like they came from a sci-fi novel. But in fact, these guys are real. They're a proven technology. They're tested on the ground. They just haven't been put on a rocket yet. So that's basically the gist of chemical rockets. If I missed anything, please do tell me in the comments. This is an open course, or this LOSC is an open university. We're open to new ideas, and we're open to any changes in what we need to do. So if I commit an error, I can just make a footnote that corrects that error. Alright, so do tell me what I did wrong if I did something wrong here. So I believe that ends our lectures on engines, rocket engines, chemical engines. I'm not sure what's going to be next on the lectures. I think I'll be continuing on relationship theory, but I think that's going to be either tomorrow or following weeks. So that'll be it for this this lecture. Hope you guys at least got a little something, got a little idea on aerospace engineering, because space is the next frontier, to be honest, folks. Space is the next frontier. We need more engineers that are passionate about space and wanting to go to space, because really that's where we should go. Okay, I'm not gonna rant further, so I'll see you guys in the next one.